Next, we talk about the mathematical representation of the turbulent terms. Okay, first of all, we need to define what turbulent is. It's actually the deviation of your values away from the mean value. So this is a very simple diagram showing you the idea. We have calculated the mean of all the values, and then the deviation from the mean, that would be the turbulent term. And then in terms of what we are observing in the atmosphere, this is showing you the idea. If we have the spectral intensity means how strong the circulations are. So for the large scale circulation representing the synoptic scale, maybe mesoscale weather systems, this is the strength of that. And then we have another peak here representing the strength of the smaller scale stuff, which we call them turbulence in the PBL. And you can see that if you do the average, for example, if you do the average over a period of 30 minutes, you will average everything in here, which means that the only signals left would be the mean flow or the large scale flow. Okay, so this is a simple mathematical method to separate the signals from the two areas in here. Okay, so we need to do averaging in the basic equations, and now I'm using just the momentum equation in the x direction to show you the idea. Okay, here is that momentum equation, and this is the total change. It could be expanded into the local change and then the advection terms. Okay, and then to study the turbulence, we need to do averaging, of course. If we don't do averaging, we cannot find this. Okay, and then do subtraction. This is the subtraction. Okay, first of all, we need to understand the notation of averaging. This over bar means averaging. Okay, we're averaging the whole equation on the left-hand side and then on the right-hand side. First of all, we need to apply what we call Randall's averaging. We have some averaging rules, actually. So the average of the sum of these two terms equals to each of their averages, and then we do the sum. So it's the order that is different in here. Okay, we do averages first, and then we do the summation after that. Okay, and then this is the other way around. So here is an example for the averaging rules. When we apply this averaging rule to this equation, we know that we can find out the individual averages for all the terms, and then that would still be equal to what we are doing in here. Okay, I think I can demonstrate that. Okay, we do the average of the whole equations, and then this is the next step. Okay, what we have applied here, we have applied the averaging rule here, right? Okay, and then next step, In this part, we are going to handle the things on the right hand side first. So I'm just going to copy what we have on the left hand side. Okay. Okay, and then what we have applied here is this averaging rule, and A being a constant. And we know that this rho naught and F are constants in the planetary boundary layer. If you want to know why this is constant, please take 4520. Okay, I'm not going to explain that in this course. Okay. And then the next step, oh sorry, I have left this behind. Okay, and then the next step is that this bar here will fall onto P only, and that's because of one of the averaging rule. Okay, this one. The average of the individual slopes equal to the change in the slopes. I think I have this line here. Okay, so if we do local slopes, we will put all the tangent lines on this black curve, and then we find out that the average of the slopes lying on the gray dashed line in here. And then this one, if we do averaging of the values on the black line, we need a range, right? If we do the average over this range, the values will be lying on this gray dashed line also. Okay, if we do the average and then we find out the slope, it will also be lying on this line also. So that's why they're equal. Okay, if you don't understand, it doesn't matter actually. You just need to use or apply the averaging rules. Okay, so I will deal with the left hand side in the next part. In the next part of this lecture. Okay. So what we have done is that we have applied the averaging rules on the right hand side. No problem here because rho naught and F can be considered as constant in the PBL, and these are the averaging rules that we have used, I think. Okay, and then the problems actually lie on the left hand side. It's more difficult to do the averaging because we have the products of the two dependent variables in here. So when we do the product here, x and y, and then we do the average of this product, what would happen? Okay, if we expand each of them into the mean and then the turbulent term, this is what we can see, and then we can expand these. There will be 4 terms. We will have the average of x and average of y, and then we also do an overbar. This overbar is coming from this one. Okay, we will have to put overbars on all 4 terms. Okay, and then the average times the turbulent term, and average times the turbulent term, and then turbulent term times the turbulent term here. Okay, and for this one, it's very easy because they're both averages. This average doesn't mean anything because they are already constants in here. So we just get rid of the top overbar in here. Okay, and this overbar, for the second term, this overbar will fall onto the turbulent term because this one can be treated as constant. This is what we can see in this averaging rule, right? If this one is A, then this average bar will fall onto this variable, this y prime variable. And this one also the similar situation to this one. And then for this one, we cannot do anything about this because this will not fall into anything. There are no averages in here. Okay, and then these two are 0 because of the averaging rules. The first one in here. The average of the turbulent terms would be 0 because it's deviation from the mean. So if you look at this graph here, we put a mean value here, and then if you add all the deviations, they will add up to 0 actually, because it's the mean, right? Okay, so we cross out the, we cross out the middle two terms, and then what we have left is that if the product, the averages of this product will be equal to the averages and then their product, we average them, each of them first, and then the product of them, plus the covariance terms of the turbulence, and then the average over them, okay? Which means that the physical meaning here is that the average conditions for the turbulence will have some effect in this equation. Okay, and we will talk about that in the next part.